Hello everyone. Welcome to the last part of the video for the review of the exam 4. This is Bob here. I'm going to illustrate how do we solve the combined loading cases. All right. So if I have a beam, let me switch the color real quick here. Black is the way. So if I have the beam and with a fixed boundary conditions, this is the wall apparently, and this is the beam, say rectangular. Okay. All right. If this is the beam, and I have a point load that acting right at the end of the beam, say at the center point right here. Okay. All right. And if the beam has a length of L, I would like to find out the stresses in the corner, at the corner of the boundary, let's say at the point H here. Okay, so what are the stresses at the point H here? All right, so to find out the stress at the point H, we have to first make a cut. Okay, so make a cut. Okay, so this is the wall. And I'm exposing myself at the point H here. Okay, this is the cut here. Okay, now first thing first, you would like to establish a coordinate system. Say this is, for instance, the y direction. This is the x direction, and this is the z direction. Okay, so once I made this cut, and of course this cut have to cross point H. Okay, I can determine what kind of load I have at point H. Okay, so if this is the load force P, all right, so let's take a look in relative to point H, where exactly is this force is at. So to illustrate where the force is at, I make an extension line, and here is where the force is at. Okay, so what I would like to do is that I would like to shift this point H here from this location all the way to the center of my cut here. Okay, so shift P. Okay, so once I made this shift, I have to observe how much distance I have traveled while shifting from the far point P here, let's say, give a name here, K, to the center point O. Okay, I would like to see how much of distance I moved. So from P was originally here, I shifted to point here. Okay, I will travel this much distance, and by decomposition, I actually will travel a distance here, say L, okay, and I'll also travel a height of h divided by 2, where h is the height of the section. Okay, h is the height of the section. Okay, so let's take a look what kind of forces I will have, right? So when I shift my P from K to O, when I travel distance L, basically I will add a moment of PL going this way. Okay, to put in a double arrow, basically I will add another moment Okay, this is basically the moment of mx equal to PL. All right. Simultaneously, by moving the forces from half k to O, I travel a distance of half h. Okay, so how much of a moment I will have by traveling the distance from k to O by half h? Apparently, I'm traveling with the same direction as my force P. Is that right? Same direction as my force P. So I don't have any moment. Okay? So on this cross section here at H, okay? So based on this drawing, what kind of forces I will have, right? So on the cut, okay, on the cut, I'll have a shear force, which is P, okay, shear force, which is P. I have a bending moment, which is PL, okay, PL, all right. Do I have any moment with respect to Y? With respect to Y, I don't. Why is that? Because my force P is parallel to Y. Okay, my force P is in parallel with Y direction, so there's no moment in the Y axis. Okay, so how about the moment caused along the Z axis? Of course, 0. Why is that? Because my P is crossing Z axis. Okay, this is Y axis. Okay, so you quickly realize that this basically saying no moment when force is in parallel or passing through the axis. Okay, in parallel or passing through the axis. Okay, so this is a critical criterion that you can use to judge whether you have acted moment with respect to certain axis or not. Okay, so with this setup, basically I identified the shear force. And to be exact, this shear force is actually in the Y direction and it's in a negative way. Okay, negative way. Okay, so I have a shear force in Y direction. To make it complete, actually, I also know that the shear force in X direction is 0. In the Z direction is also 0. Okay, so let's organize the table a little bit. Okay, let's organize the table a little bit. Okay, sorry, let me just move this whole thing. Okay, so essentially what I'm trying to do is I'm going to list all these possible forces on my plane of the cut. Okay, so I identify all the forces, and then I identify all the moments. Okay, then I can start to find out the stresses on H. So stress on H. Okay, now let's observe this cross-section cut again. Okay, and that is the boundary. Okay, so H is right here. So on this point, what type of stresses I will have? So zooming here, I will have first shear stress from Vy, isn't it? Shear stress from Vy, isn't it? I will also have axial stress due to bending moment, mx. Okay, is that right? So I have two types of stresses I will see, right? So let's take a look. What stress I will see on H? Okay, so sigma H shear, right, will equal to VQ over IB. And mind you, here this is Y, sorry, and this is T actually. Okay, so the shear force is actually P. And what is Q at point H? Let's examine. So I'm on the point H here. Okay, I'm on the point H here. This is the neutral axis. The H, right? The H should be across the line on the opposite side of the shades, which actually turns out QH equal to 0. So this is 0, this is I, T, and so shear stress at H is actually 0. Okay, so only two non-zero component Vy gives you that the shear stress generated by Vy is 0. And the moment Mx will give you a sigma H in terms of axial, that equal to MC over I. Is that right? So let's take a look at it again. Okay, the C equal to the half of the height. Okay, C equal to half of the height, right? The moment actually is PL, so this will be the moment. Assuming the width of the beam is B, so I have 1/12 BH cubed. Okay, so I flip the top and bottom, so I have a 6PL over BH squared. Okay, so now I have both the shear and the bending stress at this corner H here. So let me zoom in this point here, right? So let me zoom in a point here. Okay, then I realize that I'm actually dealing with a small element that seeing a normal stress of sigma H axial and that's it, because I don't have shear stresses. I don't have shear stresses. Okay, so the principal stress, if I want to find out the principal stress at H, that is equal to sigma H axial over 6PL over BH squared. Okay, so now we have figured out a way. To establish, right, our stresses from combined loading. Okay, and this is one example. All right, let's go back and take a look at this case. Okay, I'm going to circle this. Okay, and going to copy it and paste it here. Okay, now let's say I don't want to find the stresses at H anymore. I want to find stresses at J, right in the middle of the cross section here. Okay, so stress at J. Okay, so we'll do the same thing now, right? We'll do the same thing. So this time the cut is the same. This is the cut. This is J. Since the cut is same, I will say now Vx still equal to 0, Vy still equal to minus P, Vz equal to 0, Mx equal to PL, My equal to 0, and Mz equal to 0 as well. Okay, so with that, I would find out the stress at J. Now let's take a look. So the section is rectangular, has a width of b, height of h, and J is right in the middle here. Okay, so what type of stress I will see here? So first of all, let's see what type of stress will generate from Vy. That's the only non-zero element. Non-zero forces. Okay, so Vy will give me a stress of shear stress, so sigma J shear equal to Vq over IT. Right? So V basically is Vy, so that gives me a negative P. Okay? And Q now does not equal to 0 anymore because Q is actually half of the area now. Okay? And we know that basically this Qj equal to area and multiplied by the distance. Okay? So equal to half of BH. And what is the distance? The distance is quarter h. Okay, so that is BH squared over 48. Okay, so that's the Q there. That's the Q there. Okay, so now let's go back to multiply BH squared divided by 48 and divided by 1 over 12 BH cubed. And T in this case is the width B. Okay, so now I have basically a minus P and H goes bottom here, divided by A. This is 12, so 4, and I have a B at the bottom and have a H here. Okay, so that is my shear stress. That is my shear stress. Okay? All right. So once I have my shear stress solved, I want to find out what other stresses my bending moment gives me, right? So I have an axial stress generated by the bending moment, isn't it? Okay. So the bending moment will generate stress mc over I, where I have basically m, which is PL. This is mx, by the way. This is Vy. And c is the distance between the point J to the neutral axis, which is right here. So the distance c is actually equal to 0. Is that right? Because it's on the neutral axis and divided by I, so I have a 0 axial stress on J. Okay. So now, if I want to zoom in J, and I want to draw my small element of J in terms of Y, X, Z, I only have a shear stress. And it's going downwards. Sorry. It's going downwards. Okay. Okay. And so this is actually my tau or sigma shear J, okay, which is equal to negative P over 4BH. Okay, so this basically equal to tau J, right? Shear stress. I'll make a correction here. Sorry about this. This is basically tau H. Okay, tau J. Okay. All right, so you can see that there are several steps to follow to find out the stresses at any cross-section. Okay, so first you observe the problem, make the cut. Okay, across the point of interest. Okay, then establish local coordinate system, x, y, z. And find forces and moments, and also axial forces. if you have any. And torsions, okay, if you have any. Okay, after you find all these possible forces, then solve for stress. Okay, so that is the approach. That is the approach. Okay, all right. I'm going to show you how to solve some of the related problem using the notes I already uploaded to Canvas. Okay, so sit tight and I'll see you in 10 minutes.